Hi everyone, welcome to this channel. In this channel, we're going to know how to calculate design loads on floors, beams, and columns. Then how these loads are transferred from one structural element to another. Looking at this picture, you'll see that we have a building here, and then we have the roof beams, turning to the columns. Look at the arrow point, my mouse point. Turn to the slab, beams, columns, slab, beams, columns, slab, columns, slab, columns. So these loads are being transferred. So we are also going to know how we generate this type of free body diagram. You must have been wondering, you've been saying these things and you don't know how it's being generated from real life questions. So we are going to be calculating this and then generating this. This is like here we have the uniform distributed load, we have the point load, we have 2 point load, we have the point load, combination of point load and uniform distributed load, all on simply supported structures. We have this uniform distributed load and 2 point load with on the simply supported beam. Now we have this as a continuous beam with uniform distributed load and the point load. This is uniformly varying load. So we are going to be calculating how these things are being formed. You get me? So let's get started and understand or refresh our memory on what load transfer is and then how the loads are being transferred, the load flow plan, and then every other thing we need to know about this. Okay. So if this is the first time of joining this channel, this is the Merchant Construct-preneurs and Tutors, where you get information about engineering, clarity about engineering, construction related problems. So let's refresh our memory of what load transfer is. In my previous class, I talked about load transfer as in I related it to relay race, whereby you have a 100-meter race, you have people standing at either 20 meters or 25 meters intervals. So the first person stands on the 0-meter mark, next person stands on the 20-meter mark, or 25-meter mark, 50-meter mark, 75-meter mark, and 100-meter mark. So the person on the 0-meter mark will need to run and pass the baton to the person on the next mark, by the 25-meter mark. Same thing happens, 25-meter mark man runs to transfer the baton to the person holding the 50-meter mark. So it goes like that till it gets to the last point. So here we have, in building construction, load transfer is the essential process by which weight and forces are distributed from various structural elements to foundation and ultimately to the ground. This integrated process ensures that a building remains stable, keyword stable, safe, and functional throughout its lifespan. So what this particular statement is just talking about is just load transfer is just how loads, weights are being transferred to various structural elements down to the foundation. Like I said in this picture, we have this. This is the roof beams, we have the columns, we have the slab, we have the beam beneath it, columns, slab, beams, columns. Now here we have flat slab. That is the reason why I don't have any beam. So the slab transfers to the columns, slabs to the columns. So columns sends all this own down to the foundation. So this is what the statement is talking about. Now, the load transfer process begins with the roof. Like I said here, it begins with the roof, down, takes it, and the floors, which bear the initial loads from occupants, furniture, equipment, and environmental factors. So imposed load and dead loads, all the loads, including the winds and snow. So these loads are transferred through horizontal structural elements like the beams and slabs. You get me? From the roof down to the beams and slabs. Now these beams are designed to carry loads and distribute them to the vertical elements such as the columns and walls. You understand this now? So the loads are being transferred from one structural element to another. So from the roof down, depending on how the roof is being constructed. If it's direct, like the picture I sent here, the roof to the columns send its own down. So the individual floors now have their own slab to the beams to the columns. So now looking at how columns transfer their own load, we talk about beams transfer its own load to the columns. Now columns, which are quite critical vertical support structures, transfer this load downwards down to the foundation, so it is continuous. So it plays a significant role in distributing the weight evenly to prevent any part of the building from being too much load, which may lead to structural failure. So these columns transfer the loads to the foundation. Now the work of the foundation is the one that bears all the loads that have been transferred from the rooftop down to the foundation. So it spreads the load from the column over a broad area of soil or rock, depending on the type of foundation, whether it is shallow foundation or deep foundation. So it spreads this load and then this load is being dissipated. I hope you are following, you are understanding this process, integrated process of load transfer and the load part. Okay, so we also talk about lateral loads. Lateral loads are horizontal loads. Like for high-rise building, we need to calculate the lateral loads, like for cost of winds and other external forces. So to resist all these loads, the shear walls, bracing and rigid frames are included. So they accept these loads and then transfers it down to that load part. So these elements are specifically designed to handle horizontal forces and prevent excessive swaying or collapse. So effective load transfer in general, everything we have been talking about load transfer, relies precisely on engineering calculations and use of appropriate materials to ensure that each component of the building can handle the forces it encounters. Engineers must consider factors like load paths, material strength, and behavior of different structural elements under various conditions. So this particular statement is just talking about, even if you understand load transfer process, we need to understand that if we don't get this thing right, like our assumptions, if we don't assume right how the loads are being transferred, there'll be a problem. We might not achieve the end result. If the materials we are using now, we do not check for the material strength and other properties of it before including it, then there's a problem. If we don't know the purpose which this building is serving, there's a problem. Even this underlying soil, you need to know the bearing capacity of the underlying soil and then the weight in which this structure is going to be imposed on it. So to do that, we need to know the type of foundation we are going to make use of. I hope we are following. So let's continue with, okay, we are looking at the worked examples. Now worked examples. So we are going to know how this is the position of a slab, a beam, and a column. So you know the topic is about how to calculate design loads on floors, beams, and columns. How to design loads on floors, beams, and columns. So as it is like this now. Now the floor, this is the floor, shown below the overall depth of 225, that is the slab thickness. It should be designed to carry an imposed load. So on the floor we have an imposed load. Imposed load, like these are life loads. They are not stationary. So they are not stationary, they are movable. So we have maybe of equipment, maybe of humans, or anything at all that is not stationary, that is not permanent. So then this imposed load also includes finishes and ceiling loads of 1 kilonewton per meter. Now calculate the design loads acting on beam B3 to C3. So this is the beam, this square-like shape is this column, and then this portion of it between two beams are slab. So B3, this is B3, this portion to this portion. B2, this portion to this portion. B1 to B3, B1 to B3, this beam. And also on columns B3, column here, and also this column here. So assume that all the column heights are 3 meters. Beam weight is 70 kg per meter run, and column weight is 60 kg per meter run. So we are going to calculate. Now, this question, we are wondering why it is shaded like this. Now, how the load part, how slab transfers the load to the beam is, it transfers the load along the longer part. So let's say you have a slab that is rectangular in shape now. So the longer part, and you divide it into two. So along the longer part, that is where the loads are being transferred, like what you have here now. You see this portion that is shaded. So half of this will come to this beam, half of this load will come to this beam. For this beam here, half will come to this beam. You see the pattern is different from what is there. So half will come to this portion, half will go to this beam, half will come to this beam, half will go to this beam. So in the long run, only half of this slab is coming to this beam. On this other beam here, this half of this slab portion is coming here, half of this one is coming here. So I hope you understand. So we are going to proceed with our calculation and whatever we were given. So we are going to look at the parameters that were given in the questions. So we have the floor depth as 225 millimeters, We have the slab imposed load as 3 kN per meter square. We have the floor finishes and the ceiling loads as 1 kN per meter square. We have the column height as 3 meters, beam weight as 70 kilogram per meter run, column weight as 60 kilogram per meter run. So the parameters we are looking for from the questions: design loads on beam B3 to C3, B2 to C2, and B1 to B3. That's for beams. And then for the columns, the design loads on column B3 and C3. I hope we are following. So we are going to continue from. So the first thing first, we are going to calculate the unit weight of these materials. So we have the materials, we have the reinforced concrete from the question, and then we have steel. So for the reinforced concrete, to calculate unit weight is unit mass multiplied by gravitational constant. So unit mass of concrete is 2,400 kilogram per meter cube. Then gravitational constant is 10 meter per second square. So if we understand this, then we should understand this from our basic physics. So we have it 24 times 10, we have it as 24,000 Newton per meter cube. So converting it, so we have 24 kilonewton per meter cube. That's unit weight of the reinforced concrete material. Now for the steel beams, we have this as the unit mass of beam as 70 kilogram per meter cube. So unit weight, from our formula, we have a unit mass multiplied by gravitational constant. So multiplying 70 by 10, we have it as 700 Newton per meter run. Then we have it as 0.7 kilonewton per meter run. That's for the steel beams. So the next portion will continue. We have floor beams and columns. So for the columns, we have this unit mass of column is 60 kilogram per meter run. Unit weight of column is 60 multiplied by 10. From our formula, unit mass times acceleration due to gravity. So we have it at 0.6 kilonewton per meter run. I hope we are understanding. So the first thing we are doing is we are looking at calculating the unit weight of all these materials. Then now we are going into the loading. So for the loading, we have we still have these materials. We have the slab, we have the beams, and we have the columns. So we are going to take them one after the other. So for the slab loading, we consider dead load and live load. So the dead load on the nose finishes is part of dead load. Finishes is permanent. Plastering is permanent, so they are part of dead load. That's why we have it. So we are looking at the self weight of the reinforced concrete plus finishes load. I hope you understand. So now the self weight is the thickness of the slab multiplied by the unit weight. We are expressing in per meter square. So the unit weight multiplied by 0.225 by 24 plus 1, that is for the finishes load. So we have it as 6.4 kilonewton per meter square. Then the slab imposed load from the question, we have it as kilonewton per meter square. So ultimate load, according to BS 8110, we have it as 1.4 GK plus 1.6 QK. So when you multiply and then add together, 1.4 multiplied by 6.4, that's for the dead load. Then 1.6 multiplied by 3, that's for the imposed load. We have our answer as 13.76 kilonewton per meter square. So we are done for the slab. We are now going for the beam. So we are going to do the same thing. Now for the beam, from the question, we are not given dead imposed load. We are just given dead. So the dead load, we are going to calculate it as the self weight of this. You get me? So we are not given the thickness of the beam. So the self weight will just be this. So beam ultimate load is equal to 1.4 GK. So 1.4 multiplied by 0.7, we have that 0.98 kilonewton per meter run. I hope we understand this. So for the column dead load, from what we calculated as the unit weight. So the unit weight is the 0.6 kilonewton per meter run. Ultimate load now 1.4 GK. As we have live load, we don't have plus 1.6 QK, but we don't have live load, so we are taking it as what we are given. So 1.4 multiplied by 0.6, we have this answer as this 0.84 kilonewton per meter run. So the next thing we are going to be looking at now is the design loads. This is where the work is. So we have actually done this calculation in 3 steps. We have done the first one as units weight of the material by calculating unit weight of each of the materials. Now we look at the loading on each of these materials too. So now we are looking at design loads, how these loads are being transferred. That is where design loads are. When we talk about load transfer, if you don't understand the principle of load transfer, then we are going to be having issues with analyzing this. So for beam B3 to C3, assume that the slab is simply supported. Beam B3 to C3 supports a uniformly distributed load from a distance of 1.5 meters and is half of the width of the slab plus the self-weight of the beam. If you don't understand this statement, let's look at it from here. This is beam B3 to C3. Now I told you how the load is being transferred. This is what is the name? Along the longer span. So this is the portion of the slab. Here, this. We have this distance as 6 meters. We have this distance as 3 meters. So the longer part is this 6 meters. So the load transfer would be along the longer part, like I explained initially. So we have this as half will come to this portion here, half will go to this one. So that is the statement. What you mean by uniform distributed load from a distance of 1.5. This is 3 meters. So half of 3 meters is 1.5. I hope you understand the statement. Then, now the slab is resting on the beam. So we are going to take the load of the slab plus the weight of the beam itself. The beam also is the dead load, so we need to collect its own weight. I hope you understand. So now, beam, to understand this now, slab is expressed in per meter square, while beam is per meter run. So we need to have a uniform unit, kilonewton. So it is not, we're not going to be having conflicting units. So here now, so design loads on beam is equal to slab load, like I told you, coming from here down to this portion here, plus self weight of the beam. So we have it 13.76, that is the loading on the slab. So we want to convert it to kilonewton. No issue. So the length, this is the length of the slab, and then the width of the slab, 1.5, the load that is transferred there, 1.5, plus 0.98, that is the loading of the beam, that is the self weight of the beam, multiplied by 6, that is the length of this beam. This is the beam here, beam B3 to C3. I hope you understand. So multiplying and adding this thing up, we have it as 129.72 kilonewton. So this is the assumption we made. It is simply supported beam, and then exerts a uniformly distributed load on the beam. So this is it. This is how we arrive at this. So now, okay, the reactions now, because this is simply supported and this is symmetrically loaded, so the reactions is just half of the design loads. So RB3 equals to RC3 equals to 129.72 divided by 2. So we have it as 64.86 kilonewton. In my next video, I'm going to talk about how to calculate reactions in case we have a loading that is not symmetrically loaded. So we know how to calculate it instead of making just assumptions. The reason why I'm doing this is that it's been proven that even if you start calculating the reactions, the normal way of calculating reactions, we are still going to arrive at the same answer. So this is the rule here. So we are moving over to the next beam. We are asked to calculate. So the next beam is beam B2 to C2. The same thing, let's locate beam B2 to, this is B2 to C2. So the beam load is going to half of on this portion is coming here, half from this portion is coming here. That is a total of 1.5, 1.5. That have a total of 3 meters. That is what it is here. So assume that the slab is simply supported. Beam B2 to C2 supports a uniformly distributed load from a distance of 3 meters. Half of the width of the slab from both sides, 1.5, 1.5, 3 meters, for the self weight of the beam, what I explained here. So half here, 1.5, half here, 1.5. This is the beam we are considering. So design load on beam B2 to C2, slab load multiplied plus self weight of the beam. So following the same method, this slab load on this beam, this is 13.76, multiply by 6, which is the length, then multiply by 3, which is the width from here to here, 1.1, 1.5, 3. Then we have also this one of the width. The beam has the same width of 6 meters. So when you multiply and add them together, we have our design load as 253.56 kilonewton. And then from our assumption, this is what we have explained, that we assume it is simply supported, uniform distributed load from the slab. So this is it here. This is the width, the length of of this beam. So the reactions, as we said earlier, on B2 and C2 is the design load divided by 2, since the beam is symmetrically loaded. So move over to the next one, which is for beam B1 to B3. I hope you are following. Please, if you have any questions, you can just drop your questions or for clarification on the comment section, please. Okay, so the next thing, beam B1 to B3. Now, assuming that the slab is simply supported, beam B1 to B3 supports a uniformly distributed load from a distance of 1.5, that is half of the width of the slab, plus the self-weight of the beam, plus the reactions transmitted from beam B2 to C2, which acts as a point load at the midspan. This statement now is somewhat confusing, so we need to take it step by step to understand what this statement is. Now, let's locate beam B1 to B3 first before we do anything. This is it. This is the beam. B on grid line 1, so B1 to B3. So this is it here. So now, I told you that the slab transfers its load along the longer span, and this is the longer span. Looking at the beam, this is the slab here, and the longer span, we have this as 3 meters and we have this other part as 6 meters. So the slab transfers its load, half of the load to this. That is why it is shaded like this. I hope we are understanding. So now, what we have here is the slab load plus self-weight of this beam plus the point load. This one is at the midspan here, or at this point here. It's transferring its own load. This beam is connected to this one. These other ones too are connected, but you have reaction there, so it's just like it's fixed. But this one now that is now at the end here, we are going to consider it in our calculation as the load on top of the beam. I don't know if you understand. So it has an effect on this portion here. So this arrow B, this is beam B2 to C2. And we already have reactions at the two ends here. So this reaction at this end, they will be acting as a point load on this beam we are considering. I hope we are understanding or we are following. Okay, so that is what it is. So we have it as a normal calculation. 1 point, the slab load multiplied by the length of the slab multiplied by the width. This is the width 1.5, since we have it as 3 meters here. So the self-weight of the beam 0.98 multiplied by 6, which is the length of the beam. Then plus the reactions that we happen as point load, the reactions on this particular beam B2 to C2 that's acting at this portion here. So 126.78. So multiplying and adding all these things up, we have it as 256.50 kilonewton. Like I told you, slab beam, you need to have a uniform unit, and that is why everything is in units. So this one per meter square is not cancelled per meter. Okay, and this one is already in kilonewton already. So the reactions on B1 to B3 is still divided by 2 because it is symmetrically loaded. This is acting at the midpoint of this. So what we have on the left is the same as what we have on the right. That is what we mean by when a beam is uniformly distributed. What you have on the left is the same thing as what we have on the right. I hope we are understanding. So to do this thing now, we already said this is the point load. So this point load now is acting at midpoint. So this is 126.78. Then the other ones are the load from the slab, the uniformly distributed load from the slab. we are being considering here. So when you add this and this, okay, you have it as 129.72. I hope we understand. We are understanding this portion. Okay, so the next thing now we are looking at the next item, which is calculating for the columns. First column we are considering is column B3. And then B3, let's locate B3 on our question. This is B3, column B3 here. You understand? So column B3 is being connected by how many beams? This is column. This one from the intersection here. This man comes here. This man also comes here. That is how we have it as this here. This man comes here. This man comes here. This man comes here. So 3 beams are connecting this particular column here. So we are going to take a different turn. This is going to take a different turn from the beams we have been calculating. So column B3 supports the reactions from A3 to B3, B3 to C3, B1 to B3, and its own self-weight. Do not neglect its own self-weight. Okay, so let's take each of these beams separately and the load that they are carrying. So for beam A3 to B3, A3 to B3, we have it as self-weight divided by 2. So 0.98 multiplied by 3 divided by 2. So 1.47 kilonewton. I hope we understand this. Then for the beam B3 to C3, beam B3 to C3, the load or the reaction. So okay, let me explain this portion again so you understand this. You understand this? You get me? So now it is the reactions that we are actually looking at, because at this portion here, this intersection, this is the beam here. Reaction will be on this portion and reaction will be on this portion. For this beam, reaction will be here, reaction will be here. On this beam, reaction will be at this portion, reaction will be on this portion. So it is the reactions we are considering now. I don't know if you understand. So for this one now, we have the self-weight of the beam as 0.98. Then multiplied by 3 divided by 2, symmetrically loaded, because what you have on the left is the same as what you have on the right. So that's why it's divided by 2. So for this other portion, B3 to C3, we already calculated the reactions as, where did we calculate that first one? So the reactions B3 to C3, we have it as 64.86. I hope we are following. So for this other portion, B1 to B3, what we have, B1 to B3, we have 128.25 kilonewton as the reaction that is on each of this portion. So 128.25. So that is how we got this. So self-weight of the column now will now be ultimate load multiplied by height. 0.84 multiplied by 3, we have 2.52 kilonewton. So the design loads on the column B3 is now 64.86 plus 128.25 plus 1.47 plus 2.52. We have it as this portion. I believe we understand what I have written here, but okay, trying to solve the second column, we understand better. This beam, what is exerting on this column is the reaction. This beam, what is exerting on this particular column is the reaction at this portion here. This beam also has the reaction on this portion here. So we understand, Abi? Yes. So let's move on to the next one so that we understand fully what this is all about. So for the column C3, this is C3 here, locating C3. This is C3, column C3. So we have this beam connecting beam C1 to C3 and beam B3 to C3. As we have here, C1 to C3, B3 to B3. So now the reaction of this beam at this portion here, that's what we are considering. The reaction of this beam at this portion, that's what we are considering. So you get, and then its own self-weight. So beam B3, reactions from beam B3 to C3, C1 to C3 and its self weight. Hope you understand it. So we are going to take it bit by bit now to understand what this is all about. I hope we understand it. So now, beam C1 to C3. This beam C1 to C3. Support LC2 from beam C1 to C3 plus self weight of beam C1 to C3 divided by 2. Let us understand this thing and know what we are doing. You know, we did not calculate this beam while we are considering what we calculated initially. So now, looking at this, we have a reaction at this portion, we have a reaction at this portion. Then this beam B2 to C2 is actually acting at the center of this beam. So what we have on the left, 3 meters distance, and what we have on the right, 3 meters distance, is the same. That is why we are dividing by 2. Assuming it is not uniformly distributed, we are not going to divide by 2. Let's understand this thing. It is only when it is symmetrically loaded that what we have on the left is the same as what we have on the right. That is when we are dividing by 2. I hope we understand it. So assuming we had calculated this for this beam, we don't have any issues with coming down. So what we just need just to pick the reaction at this portion here and then move on. So now we are going to do a mini long calculation. Okay, so now, so the support on RC2 at this portion here, this reaction here is acting on this. Is acting on this. And then we have it as 126.78 reaction there. Then the self weight of this beam, because we did not calculate it initially, when we calculated from it, we will not have any stress of going through this portion again. So we have it as 0.98 multiplied by the total stretch is 6 meters, 3 plus 3 is 6 meters. Then all divided by 2 on how we calculated for this other portion here. Like what we did here, we did not calculate for this before. So what we did is the self weight of this beam is symmetrically loaded divided by 2. There is no external load acting on this. So we move, continue. Then so after multiplying and adding and dividing, we have it as 66.33 kilonewton. So beam B3 to C3, we already have the reaction at this particular portion here. So we just picked it and placed it there. So the self weight of the column will now be ultimate load of the column multiplied by the height. So we have the height is 3 meters, and we have it as this. So hence the load on column C3 to C3 is now 64.86 plus 66.33 plus 2.52. So we have this value as this. So we have successfully calculated for everything that we are asked to calculate for design loads on beam B3 to C3. Yes. Design loads on B2 to C2. Yes. Design loads on B1 to B3. Yes. Design loads on column B3. Yes. Design loads on column C3. Yes. So we've calculated this successfully. So I believe with these calculations and this explanation that I've made, we are going to find it easy to be able to get all these free body diagrams that we talked about from here. Can you see now we successfully created this, we did this, we did this. So depending on how the questions come, this is real life something. So no matter how the questions come, you're going to be able to know, okay, this is a point load acting on this portion here. This is a point acting on this portion here, point load and uniform distributed load. So I believe we'll be able to understand this. So in conclusion, load transfer in building is a complex and critical process that involves the coordinated efforts of multiple structural components working together to maintain the building's integrity. So proper understanding and implementation of load transfer principles are essential for design and construction of any safe and durable building. So what this statement is talking about is all the structural elements, whether it's a column, the beam, it's a slab, they work hand in hand to ensure that the building's integrity and safety is maintained. Then, while you are the one designing, you should be able to understand load transfer principles, the load parts, how they are being transferred. Because if you don't interpret this thing well, you will not be able to you don't make the necessary assumptions, then you'll not be able to understand exactly how these loads are being transferred and how these loads are being considered. So, in a nutshell, we are able to calculate the load, design loads on each of these software elements, and also how they are being transferred. So if you got value for this lecture or video, kindly like this, share, and also subscribe to this channel, the Merchant Construct-preneurs and Tutors, where you get value, engineering, you get information about structural engineering, especially all those calculations, all those things that are like that are too hard, or like too difficult for you to understand. You get them explained in bits how all these things are being done. So kindly click on the like button, share and subscribe to this channel, the Merchant Construct-preneurs and Tutors. See you in my next video. Bye.